Hey there, everyone. My name is Samantha Henningsen. I am a project manager with ALS Environmental Air Quality Laboratory, and today I'm going to talk to you about an overview of siloxanes, specifically in landfill gas and biogas. As far as an overview of what we're going to talk about today, I'm going to give you a brief background of ALS Environmental, what we do, what we're about, and then I'm going to jump right into siloxanes. I'm going to talk a little bit about the chemistry of siloxanes, as well as why we should worry about them, what makes them compounds of interest to people specifically in the landfill gas and biogas industry, as well as wastewater treatment industry. I'm going to go a little bit into current regulations that are out there, as well as talk about available methods, methods that you would find in commercial operations if you wanted to analyze for siloxanes. From there, I'm going to talk specifically about ALS's sorbent tube method, give you a brief background as well as how to sample utilizing that sorbent tube method if you were interested in using us as a laboratory. And then I'm going to go into a few case studies with people that have used our method as well as comparative studies, and then go into frequently asked questions and conclusions. So let's go ahead and get started. ALS Simi Valley is a 20,000 square foot facility located in Simi Valley, California. We were formerly Columbia Analytical Services. Some of you might know us as that if you have done any analytical work with us. And we, as a lab, as our particular location, we specialize in air analyses. As far as ALS Environmental as a whole, we're an international company based out of Australia. We have 14 labs in the US and Canada, but our particular laboratory focuses on air analyses. We do low-level environmental work, remediation, fence line monitoring, ambient air, vapor intrusion. We're DOD and we're NELAP certified, but we also have a specialty market that's specifically geared towards landfill gas. As far as our areas of expertise are concerned, we can do things like permitting and compliance, things like Tier 2 monitoring or 40 CFR testing. We can also do energy content. That would be things like BTU testing or maybe methane content. And then methane content can also fall under gas composition. Now, gas composition could be things like if you wanted to know the oxygen or the carbon dioxide content of your gas, if you wanted to know your percentage of methane, things like that. And we can also analyze for a number of other fixed gases, as well as VOCs and hydrocarbons. And then finally, we kind of have this niche market for odor and nuisance testing. And while I won't talk much about odor and nuisance testing, we can analyze for things like amines, volatile fatty acids. We can analyze for sulfur-containing compounds as well. And so we really can round out your landfill gas analytical needs just in one particular location. As far as the siloxane method is concerned, we brought it online in 2011, specifically for landfill gas patrons. We had a number of clients coming to us asking about siloxanes, and so we brought a method online to try and meet that need. And we've been running regular samples since 2011. So, siloxanes, what are they? Well, siloxanes fall under the volatile organic compounds grouping. The word siloxane is derived from the words silicon, oxygen, and alkane, and so it's kind of a cutesy little combination of the three words. And the compounds are labeled according to the number of silicon and oxygen bonds. Siloxanes fall into two primary categories, which would be cyclical siloxanes. And so for those of you that are familiar with siloxanes, those would be labeled with the D symbol. So D1, D2, well, not D1, D2 through D6. And then you also have the branch chain siloxanes, and those would be the blue colored siloxane on the left, and those would be your L or your MM, MDM compounds. While siloxanes aren't necessarily hazardous to inhale, they do have oxidative properties, and so when they are in the presence of oxygen and heat, such as in combustion, they will combust into silicon dioxide, carbon dioxide, and water. And this silicon dioxide is otherwise known as silica or sand. And so then the sand can end up building up on a number of different pieces of equipment. So why should we worry about them? Well, while they don't necessarily have any hazardous effects to human health, they do in ppm levels in landfill gas, which is what you usually find them in, is ppm levels. They will, in essence, oxidize in your post-combustion systems, and they will end up depositing this silica onto your equipment, causing performance and maintenance problems. Now, commonly affected equipment could be things like cylinder heads, pistons, turbine blades, heat exchanger surfaces, and boilers. And they could end up causing symptoms such as wear or imbalance. They could cause fouling. I have some anecdotal information from a landfill operator that I used to work closely with that says that the engine power reduction could be as much as 10 to 20%, and or you could have, as much as twice the required frequent motor oil changes of your engines. And so ultimately that could lead to potential engine breakdown and, again, increased operating costs. So siloxanes end up causing you to spend more money in the end. For the visually inclined, the next couple slides are going to be a couple pictures. So as you can see, the white dust on the engine pistons are silica deposits. This is a really good example of some of the more common things that we see are buildup on engines. And, this powder just ends up building up until it causes failure on the engines. As far as turbines and microturbines are concerned, they are some of the most susceptible pieces of equipment because they are extremely temperamental, especially as it pertains to siloxane buildup. So, as you can see, that microturbine on the right-hand side looks like it's been underwater or something. It's just so covered in dust. And finally, this is a picture of a boiler, and it's got some pretty significant buildup on its inside. So siloxanes, where do they come from? Where in the landfill? Where in the wastewater treatment plant? What causes siloxanes to be so prevalent and to be such an issue for landfills? Well, first and foremost, they come from a number of household products. They are used to smooth, to soften, to moisten, to make things glide on more easily. They're also used as for water repelling, like windshield coatings and things like that. And you pretty much can't go down a drugstore aisle without finding a significant number of products that have siloxanes in them. So in essence, we use these products in our house, we throw the products away, they end up in landfills, and then using the volatility of the siloxanes, they end up in the landfill gas. They're also really common in plastics and adhesives, and that's mostly because they give plastics a bendable property. They make them more malleable. They're not so rigid when you have siloxanes as part of the mixture. And they're also used in a number of lubrications and paints and things like that. And then finally, and kind of most interestingly, is they're also used in synthetic food products. Siloxanes are used in a number of fat-free products because it gives people the mouthfeel of fat without the calories of fat. And so you will find it commonly in a number of fat-free and low-fat foods, as well as siloxanes are commonly used as an anti-foaming agent in fried foods. And so they'll add these siloxanes to the oil to keep the foaming down during the frying process. So, current regulations. Well, I hope I'm not pulling your leg by saying that I was going to talk about current regulations, but unfortunately there are no state or federally promulgated regulations at this time. Unfortunately, siloxanes are ultimately more of a manufacturer nuisance rather than them actually being hazardous, i.e. being dangerous to humans, being dangerous to animals, or even necessarily being dangerous to the environment. And ultimately, without the whole combustion process, the siloxanes really are fairly harmless. There is an ASTM group that I am a part of that was tasked with creating a siloxane method, and it's going to be in the group DO3, which is the gaseous fuels group. And I imagine that the method will probably be promulgated in 2016, so I would look at that or stay tuned for that. Otherwise, there are a number of commercially available methods that I will go into in later slides. So even though there are no federal bodies that are regulating siloxanes and there are no federal bodies that have methods for siloxanes, there are a number of different siloxane methods that are currently available. So let's go into commercially available methods. Just as a visual overview of what methods are out there, they're really separated into your collection devices. And we'll go into more detail, but ultimately, if you're going to analyze for siloxanes, you're going to be doing it using one of these 5 collection devices. We have the sorbent tube that's in the top left-hand corner. That's what ALS uses. And then if you're going clockwise, you could collect in a Tedlar bag, mineral oil, using a Summa canister or a methanol impinger. I created this table to show just an overview of what is required between ordering, collection, and ultimately shipping. So as far as the methods are concerned, they're really grouped into 3 different categories. You have your Tedlar bag and your Summa canister, which are considered whole air methods. That means that you would just collect the air as is. It doesn't absorb to anything. It's not bubbled through anything. And then from there, you would send that physical air sample to the lab for analysis. You also have a sorbent tube, which uses adsorption onto a solid media. And in essence, you would pass your air through the tube. The siloxanes would adsorb onto the solid sorbent, and then everything else would go straight through. And then you have methanol impingers and mineral oil, which is where you're bubbling your air through a solution of some kind, and the solution is what is adsorbing your siloxanes. So those are the 3 main categories. As far as the required sampling time, it's really based off of 2 categories. You have your instantaneous. So the nice thing about Tedlar bags and Summa canisters is that sampling is relatively instantaneous. You would just hook up the sample to your gas source or your sampling probe or whatever you wanted to analyze, and you would have an instantaneous sample with no real sampling time involved. And then you also have the time-integrated samples, which would be anywhere from 30 minutes to 3 hours, depending on what methodology you're following. We have the ease of use requirements, which is it's really an objective statement. It's based off of things like how much time is involved in training sampling personnel? How long does it take to sample? What are the temperature requirements? Are there any? As well as if it requires the Department of Transportation hazardous shipping. Now, Tedlar bags and Summa canisters are easy because the instantaneous sample and they don't require a cooler. The mineral oil and sorbent tube are medium because they are time-integrated samples. They do require a little bit of training on the personnel front. And then the methanol impinger is considered difficult because it has some training. Again, it does require some time, but ultimately it has a temperature requirement, which means that you have to ship it in a cooler. And so it could be, it's time sensitive as far as getting the samples to the laboratory. And then the final thing to note, which is something that we at the lab always try to instill in the client, is does your sample shipping require the Department of Transportation hazardous shipping requirements? Now, even though Tedlar bags and Summa canisters are extremely easy to sample, they're extremely difficult to ship, especially if you are dealing with landfill gas. Now, landfill gas is typically, 40% or more methane and 38% or more methane of any sample means that it is subjected to the Department of Transportation hazardous shipping requirements. Now, the nice thing about the mineral oil in the sorbent tube is that the methane passes straight through the tube. It's not adsorbed. The material, both the mineral oil and the sorbent inside of the tube, are not hazardous, And so you can just ship those standard overnight, ground, whatever shipping methodology you want. And then the methanol impinger, while the methane does travel through the impinger, the methanol itself is considered to be a hazardous good. And so you would have to ship it as a hazardous good as well. As far as the analytical concerns are, there are a number of different potential compound lists that you would see. The average is somewhere around 8 compounds, which would be L2 through D6, and then trimethylsilanol. Those are, usually the most common, but there is a number of different methodologies out there. Now, the thing that's interesting about this is you'll want to always look at the approximate milligrams of silicon per meter cubed. Now, this is the approximate milligrams of silicon per meter cubed using the molecular weight of D4, because D4 is the most commonly found siloxane in landfill gas. And the thing that is interesting about this is that you'll want to compare this value with whatever your engine spec or your turbine or your microturbine spec is for siloxanes, because as you can see, many of the approximate RLs, reporting limits that you'll see, are actually higher than the siloxane limits as dictated by the vendor, by Caterpillar, by Jenbacher. And so what you'll want to make sure of is that when you're taking a sample and you're getting the results back and it's saying, oh, you're all clean, that doesn't necessarily mean that you're all clean. It just means that there's a level that's below the reporting limit of the laboratory. And so you'll want to always make sure that you're cognizant of that before you choose a lab. Okay, so just to round out the sampling overview. Now, impingers are unfortunately difficult to sample. They're medium in weight, they require hazardous shipping and a cooler, and they have moderate reporting limits. As far as sorbent tubes are concerned, they're moderate to sample. It does require a little sampling personnel training. They're lightweight and easy to ship. They don't require any hazardous shipping or a cooler, and they have low reporting limits. The mineral oil is moderate to sample. I've heard from some clients that it is fairly easy to sample, and that's not a problem, but the boxes are heavy to ship. They don't require hazardous shipping or a cooler, but they have high reporting limits, comparatively speaking. As far as the Tedlar bag is concerned, it's easy to ship and lightweight. It does require hazardous shipping. However, there is no cooler, and they have moderate reporting limits. And then the Summa canisters are easy to sample. They're relatively heavy to ship. They require hazardous shipping, however, no cooler, and they have moderate to low reporting limits. So let's go into the ALS Tube Method 101, sampling and overview. So what would happen if you decided to call ALS and you wanted to do a siloxane sample with us? What would you do? Well, the first thing we would do is we would send you a sampling kit, which would include a rotometer, a pre-prepared slipstream, nuts and ferrules, a labeled calibration tube, and a sample tube as well. So you would have a tube to calibrate your flow, and then a tube to actually take your sample with. And then there would be connecting flexible tubing, which would connect the calibration tube with the rotometer, and then there would be flexible tubing on the slipstream. And the slipstream we'll talk about in the next slide. As far as the slipstream is concerned, it's really just a way of letting off excess back pressure to account for variability in flow. Now, we don't necessarily know how much your flow is coming out of whatever outlet port you have, and so the slipstream is kind of a low-tech way of making sure that there's no excess back pressure on the inlet of the tube. So what would happen is you would hook up your sampling stream to a set of tubing. You would attach the tubing to the slipstream and then attach the slipstream to the sample. Now, the slipstream should be at the bottom of your sampling train, and the reason being is because if you have any excess moisture in the tube, especially if you have visible droplets, this would ensure that the droplets would build up at the bottom and they wouldn't build up on the back end of the tube. Now, when you're calibrating the flow, because the flow recommended is 200 mils a minute, so let's say that your flow is a liter a minute coming out of your outlet. So rather than having to lower the flow coming out of your barbed fitting or whatever your outlet is made of, you can just open the bottom of the slipstream. There's a little cap down there, and then that will let off any of the excess flow without cross-contaminating the sample, as well as, without having to do too much to the sampling. As far as the transit to analysis is concerned, the shipping temperature is ambient. Again, you don't need any cooler. Again, there's no hazardous shipping requirements. The tube and the kit weigh under 5 pounds, so return shipping is light and easy. And all of the pieces are plastic, so you don't have to worry about anything breaking. As far as the laboratory considerations are concerned, the hold time is 14 days. Between receipt and getting your results, the standard turnaround time is 10 business days, so it's about 2 weeks. And our compound list are the 8 siloxanes, L2 through D6, and trimethylsilanol. And as far as reporting is concerned, we report it in 2 units. We report it as the siloxane, so we give you the value as L2, as L3, as D4, D5, etc. And then we also quantitate it as silicon. So we take the ratio of the number of silicon atoms and then the ratio of the molecular weights, and we give you almost a value that's like the contribution of each compound to the potential of it creating silica. Okay, so for the interesting part, let's jump into some case studies. The first case study has to do with when we were doing our initial method development of the sorbent tubes. So the internal study was led in 2011, and it was conducted at a local landfill. As far as the landfill is concerned, they flared 80% of their gas, and 20% went into a condenser, and then they used it on a few of their engines in-house. So as far as what we were collecting raw, untreated landfill gas. Now, the methodologies that we utilized when we were doing the internal study included canisters, the treated carbon sorbent tubes that we ended up utilizing, as well as impingers. This is a basic comparison of the siloxane recoveries that we saw. Now, the landfill itself didn't want us to share the physical recoveries, so I created a concentration ratio, which was based off of the percentage of the largest recovery. Now, as far as the largest recovery is concerned, that looks like it was D4 in the impinger. So, as you can see, it looks like from the raw untreated landfill gas that the trimethylsilanol, D4 and D5 were the greatest offenders as far as siloxanes are concerned. And that is extremely typical as far as landfill gas is concerned. I believe that it comprised almost 80% of the total mass quantitated for all of the methods. And L3, L4, and L5 were relatively negligible. They were, less than 5% of the overall mass. As far as the canisters are concerned, we noticed that all of the recoveries of the siloxanes were lower than A, all of the methods combined, and B, what was most interesting was that they were usually significantly lower than the average. So that was something that ultimately made us decide that we were not going to move forward with the canister method, was because of the biased low recoveries. As far as the impingers are concerned, the recoveries were really good for D4 and D5. However, unfortunately, when you are absorbing an alcohol into an alcohol, you can't analyze for it. And so the trimethylsilanol is relatively unassumed in all impinger samples. So that was a big downfall of the reason why we didn't go with impinger methods. And finally, we have the sorbent tube. The sorbent tube had good recoveries compared to the average. As you can see by the standard deviation, they had good recoveries in comparison to all the other methods. And again, as far as the standard deviation between the sorbent tube and the average, the deviation doesn't vary by greater than 5%, which under any other typical protocol is concerned that would be considered acceptable in any QC criteria. So this table and graph are a comparison of the percentage recoveries of each of the target analytes, trimethylsilanol L2 through D6, as compared to each of the recoveries from each of the methods. So what I did was I created a value of 1 for the ratio, and I made the sorbent tube, which was the most median and average recovery, as a ratio of 1, and then I compared the canister and the Impingor values to the sorbent tube. So this doesn't necessarily, it's similar to the last graph, but it's not necessarily considering the abundance of each of the analytes, but rather the way, the precision of the methods as they compare to each other. So as you can see, again, the canister looks like it's biased low. It's lower than, it's lower than the sorbent tube, and it's pretty much lower than the sorbent tube and the Impingor for all of the methods. While the Impingor is definitely comparable, again, it doesn't have any trimethylsilanol capabilities. And then ultimately the conclusions are D4, D5, and trimethylsilanol are the primary siloxanes of concern. L3, L4, and L5 were relatively negligible and can be listed as non-important compounds comparatively speaking. And ultimately our goal was to identify which one was the best sorbent or the best collection device, which we decided was the sorbent tube, as it was the most comprehensive of the methods and it had the highest and best overall recoveries. So as far as case study 2 is concerned, this was a client collection case study. It happened in a landfill in Oregon, and the landfill gas samples were taken to support an agreement with Caterpillar Financing. The client was ultimately an operator at a facility, and they collected and shipped mineral oil samples initially. So when they got the results back from the mineral oil samples, they were higher than they expected, and they were also higher than the recommended limit as given by Caterpillar Financing. The limit was, for reference, 0.6 micrograms per BTU. So with the siloxane results being higher than they expected and higher than the limit, they were very concerned. And the reason being is because the engine was not showing any physical damage, it was not showing any visual damage, there was no major siloxane buildup on the engine, and so they were wondering how the values could be. I believe the values were 3 times higher than the Caterpillar limit, and how these values could be so much higher than the limit outlined by the manufacturer, and yet they weren't experiencing any any engine breakdown, any increase in motor oil changes, etc. So they decided to run a comparison of 3 methods. They did our sorbent tube, they did the mineral oil again, and then they did a Tedlar bag sample. And these are the results. So the table on the top is just a comparison to tell you that ultimately the method, there were 3 different collection devices, 3 different analytical instruments, the compound lists were a little different, but ultimately you could get a microgram per BTU value from all of them. And as you can see in the results comparison, the mineral oil is significantly higher than the Caterpillar limit that you can see in that thick red horizontal line. And the Tedlar bag and the sorbent tube were both under that limit, which corroborated the fact that the mineral oil is either biased high or there was something wrong with the methodology. But the Tedlar bag and the sorbent tube values were, again, both below the Caterpillar limit, and they compared within 5%, which would be, corroborating evidence that they were under the limit and still within the specs as outlined by Caterpillar. So, why is there variance among method results? We've seen from both of these case studies that there is quite a bit of variance, and it is a question that we get at the lab fairly regularly. But what is potential reasoning for why there's so much variability? Now, the answers I'm going to give you aren't necessarily really good ones, but ultimately it just comes down to the fact that there are so many different variability. There's so much variability in all of these methods, and ultimately it's because each lab has developed their own in-house method. Each method has its own sampling media. They all have their own analytical instrumentations. They all have, potentially different calibration standards. You could use air standards or liquid standards. The target analyte list is different, and that is probably one of the more common reasons why the values differ, is when you're getting a total mass silicone compared to an 8-compound siloxane report, it's almost like comparing apples and oranges in many ways. And so that's something that you're going to want to take into consideration. Again, the reporting limits could be different. You could be analyzing a method with really high reporting limits and it's telling you that nothing's there, compared to a method that's got really low ones and it looks like there's a ton of stuff in there. But ultimately, you're just dealing with two different sets of reporting limits. And then finally, there are results calculations and reporting formats that potentially could cause confusion in the variability of results. So the final portion of this presentation is just going to go into some frequently asked questions that I personally get in the lab regularly, and from here maybe we can offer some solace to those out there who still have some questions. So the first question I get that's fairly regular is, how was the compound list determined? What made you go with an 8-compound list plus trimethylsilanol? And ultimately, it was found that in our extensive literature search that L2 through D6 and trimethylsilanol were A, the most frequently referenced siloxanes in literature, and B, they were also the most prevalent in landfill gas and in biogas and wastewater treatment plants and areas that have combustion systems in which siloxanes are a big deal. Now, I listed here some paper references that were used in our initial investigation, and as you can see, there are a number of different citations. There are academic citations, there are SWANA landfill gas, WEFTEC, LMOP conference citations, and we're not reinventing the wheel here. Siloxanes have been an issue to landfills for a long time. We were just coming in and developing a method, and ultimately these 9 compounds were the main compounds of concern. So that's why we chose that compound list. So how was the method validated? How did you go about proving that the method was valid, that it was correct, that it was accurate, especially in the face of many methods that don't end up correlating, as you could see with that mineral oil versus the sorbent tube versus the Tedlar bag method. Now, since we are a NELAP and an AIHA and a DoD lab, we have a lot of experience with method validation. And so we actually followed OSHA's Organic Chemicals Air Sampling and Analysis Guideline. And this figure that I have down on the left-hand side is actually directly from that method. It goes through exactly how to validate your sampling procedure. It shows you how to validate your analytical procedure, and then it shows you how to validate the overall procedure. And so we ended up following this start to finish in the validation of our process. And when clients ask, this is one of the more common ways that methods will be validated, is by this kind of protocol. So that's what we utilized. And finally, how do environmental factors affect sampling? How does inclement weather, especially cold climates, how does that affect sampling? Well, in cold climates, you do have potential loss due to tubing adherences. Now, siloxanes are not extremely volatile compounds, so when it is cold out, you will experience lower siloxane concentrations. And so what we normally recommend to clients is that in colder climates that you use insulated or heated tubing, or that if you don't have the ability to use insulated or heated tubing, that you make the sampling train as absolutely short as possible so that you don't experience the loss in the tubes, because there is less surface area to lose sample. We also do offer sampling in Tedlar bag, and so some clients do opt to do that in cold weather as well. As far as warm climates are concerned, there's potential loss due to moisture. Obviously, when it's hotter, especially in those humid areas, D3 and trimethylsilanol are soluble in water, and so if you do have increased humidity or increased moisture in your samples, you could experience loss from that aspect. We do analyze for siloxanes in water samples, so you could always collect the condensate and then send it to us for a full analysis. So that's, what we would recommend if you were worried about potential loss due to moisture. As far as high humidity is concerned, again, that goes back to the warm climates, but there also could be water buildup inside the tubes that could cause tube blockage. And so while it won't necessarily cause any issues because the sorbent is hydrophobic, you could end up causing, messing up the overall volume that's going through the tubes by blocking it with the water. So we would recommend either doing a water knockout or collecting it using a Tedlar bag. So just as a basic conclusion of what I talked about today, we went into the chemistry and the prevalence of siloxanes. I talked a little bit about why we should worry about them and what causes them to be so troublesome to landfills and wastewater treatment plants. I said that there were no current regulations, but there might be in 2016. I also went into a number of commercially available methods, including the ALS sorbent tube method. And then I talked a little bit about case studies and method variability, and then went into some frequently asked questions. So thank you for taking the time to listen to this webinar. Again, my name is Samantha Henningsen. I'm a project manager at ALS Environmental. Feel free to give me a call or drop me an email with any questions that you might have. But until then, I hope you enjoy the rest of your day. Thanks.